When we're dealing with numbers, our primary definition of a number is as a point on the number line. So if I put any kind of unit on here, I can extend this line as far as I want and put every number on there. Every quantity that exists goes with a point here. So if I zoom in right here, I can decide what value of that point is. So if that's 2, 1's about here, so that's maybe 0.5 or 0.52, maybe 0.60031, right? As far as I want to zoom in, I can figure out what that point is. And most of the time, that's going to be, as we're dealing with numbers, either a whole number. In this case, it's positive, so it's not going to be a negative number. It's either going to be a whole number or a rational number. Again, either positive or negative. I should include negatives on here. But there are two situations we deal with already that you've dealt with in high school where we're not going to get a rational number. And they both come from geometry. First, what is the length of the hypotenuse here? Well, we don't need to prove it here. We'll just take it as truth that the Pythagorean theorem is true. And we can say 1 squared plus 1 squared equals c squared. We'll call it c for now. 1 times 1 is 1. 1 times 1 is 1. 1 plus 1 is 2. So it's certainly possible to measure out one unit, whether it's an inch or a meter or whatever. That's clear. If we have a scale on our number line, we can get 1 to be this distance. All right, and then 1 distance. Make a right angle. There are all sorts of ways, practically speaking, to make that happen for sure. Then if I want to run a string along here, I know this length of that string. If I square it, I'll get 2. The question is, what is that distance? I can try to spin it around. So this is hard to do. It's easier on the actual smartboard. I can rotate. But if I put this here and kind of tilted this down so it touched the page there, I can show that, I guess, make a triangle here. Take my 1 and instead put it this way, and then the other one that way. There's my 1 and 1. And clearly the hypotenuse is longer than these two sides, so 1 isn't going to be long enough. I need a little bit more. That distance we call the square root of 2, and we'll talk more about roots in Module 2. This amount is not equal to any ratio of whole numbers. And again, we can't prove that here. It takes a little more theory behind it. But there's no set of integers that's exactly equal to this. Now I can get close. If I make my units here small enough, I can get really close to that. And if I go to the nearest millionth or billionth or whatever, however small I want to get, I can get arbitrarily close, but never exactly equal to the square root of 2. That makes it not a rational number. So we say square root of 2 is irrational. And then the other classic example here, for every circle, we can make a ratio of the circumference to the diameter of that circle, and that gets a name we call pi. So if I have a circle that's 1 inch across, I take my compass and set the length between, or width between the pointy part and the pencil part at 1/2 inch, and I spin it around to make this circle. D is 1, and that circle here has a distance of pi. If instead of just graphite flecks on a page, if I make a circle out of cardboard or paper and I coil it up so that it's 1 inch wide, right, like a 1 inch pipe, but maybe paper that I could unfurl. If I uncoil that, if I take that circle and I kind of roll it out, that's going to reach there. It's a little bit more than 3. It's not quite 3 1/4. That does not equal 3.14. It's 3.14159265358979323846264332643327 and so on forever. This goes on forever. And no matter where I stop it, 10 decimal places or 100 decimal places, it will never be exactly equal to pi. 3.14 means 314 hundredths, right? That 4 is in the hundredths place. That's an equal sign here. This rational number, decimal form or fraction form, is not equal to pi. This, chopping it off at the 6, not equal to pi. Pi is irrational. And we'll see with lots of roots, we'll get irrational numbers. There are other famous irrational numbers, like E, that we'll come across later on after this math class. But in general, these values still have, not in general, these numbers do in fact have corresponding points on our number line. So there's our last set that we're going to deal with here. The fancy R, the R with the extra line on it. This set R is all the values that correspond to a point on the number line. We call that the set of real numbers. So as we look at our set of circles here, we've got the natural numbers. If we include the natural numbers and their opposites, we have the integers. If we make ratios of all the integers, we have the rational numbers. And if we include the rational numbers and these irrational numbers, we have the real numbers. Most of the time, if we don't specify otherwise, our algebra is going to deal with real numbers as the possible inputs. In our everyday lives, sometimes we're restricted to one of these other things as we're talking about it. Right? When I say my son is 5 years old, I'm really dealing with natural numbers. I'm not allowing for 5.1 years old or 5.9 years old or 5 2/3. I'm just saying he's somewhere between 5 and 6. Those are my only choices. No one says their daughter is pi years old. Right? And then we'll get into different contexts for each of these. But for now, you need to know the names of these. You need to know how they relate. That this thing, whether we see it in the circle set form or purely symbolic, we say that is contained within that, which is contained within that, which is contained within that. Those are the 4 sets of numbers that we need to care about. And we'll deal with subsets of these, say positive real numbers or even real numbers or real numbers between 2 endpoints in later sections. Right? So just on that last bit, we've already talked about this kind of set theory. We can have the interval from -3 to -1. That's a subset of the full number line. Right, I'm just looking from -1 to -3, excluding the endpoints. Pretend that actually, there we go. Right, so that's a subset of the real number line here. And we'll deal more with that in later sections.